So still in chapter 8 lecture, now going to focus a little bit more on ionic bonds and specifically how we can calculate how much energy we're talking about in that bond. So on the top of this page, if you want to write ionic bonds again, and what we're going to focus on is the forming of the ionic compound, what different steps that need to take place. So a big focus this year has been on just getting more of the details of some of the chemistry that we've been talking about, even from first year. So what we're going to talk about is something called the Born-Haber cycle that kind of details out step by step where does that energy come from and all of the different components that have to take place. So the first definition that's going to be new is going to be what we call lattice energy. And lattice energy is the energy needed to separate 1 mole of a solid ionic compound into its gaseous ions, okay? So let me put that in a formula. So if I take sodium chloride ionic compound in a solid form, and I break it up into its 2 ions in gas form, this is what it's called, its lattice energy. How much energy does it take to put those ions essentially together and form that ionic compound? Now, please note that lattice energies are always positive. They are always what we call endothermic, meaning in order for you to separate out an ionic compound into its ions, you're going to have to put energy in. And so that's going to be key in your understanding here. So what I have for you is kind of a schematic for step by step, how do we get the amount of energy it takes to form an ionic solid. So realize that we're always talking about its elements, okay, at 25 degrees Celsius, what is their normal state of matter, going to an ionic compound. That's really what we're looking at for this type of problem. And this is going to be using our idea of Hess's law that we talked about in thermo, and the fact that you can add up all of the energies, whatever the equation happens to be. So what I've given you is essentially the step-by-step. I just haven't given you the numbers in your notes, so if you want to copy this down. So if I'm taking solid sodium, I need to get it in the gaseous form. So that's going to require some energy. So that is what we call heat of sublimation. So sublimation is going directly from a solid to a gas, and that's going to take a certain amount of energy. For this case, it's about 108 kilojoules. Then once I have formed the sodium in the gas form, I need to make it an ion. So I need to make it a cation. So I'm talking about ionization energy, which we just talked about in chapter 7. So how much energy does it take to remove that first electron? It's about 496 kilojoules of energy. And again, these numbers will be given to you. That's not something you're going to have to worry about. Then I have a half a mole of Cl2 gas. A reason I have a half a mole is because then once I separate it out, I have a complete mole of 1 chlorine atom in the gaseous state. So essentially what I'm doing there is breaking the ClC bond. And since it's only a half a mole, it's about 122 kilojoules of energy. Then I want to make Cl essentially the anion. So I need to add an electron, that is the electron affinity. Again, another trend we talked about in chapter 7. That's about negative 349 kilojoules of energy. So then we have one last thing that we could put in this equation, and that is essentially the lattice energy of sodium chloride. So there's a table of these that you can look up. But the reason this one is negative is because we are talking about the ions making the solid, not the other way around. The definition is the solid going to the ions. So just keep that in mind. That is why it is a negative. So if I were to add these all up, okay, certain things would cancel. So this would cancel this. Sodium ion would cancel sodium ion. 1 electron cancels 1 electron. The CO cancels Cl. Cl minus cancels Cl minus. So I have Na solid left. plus 1/2 Cl2 gas goes to sodium chloride solid, which is exactly what I was asked to find. So all I have to do is add up these energies, and I end up with a negative 411 kilojoules, which is an exothermic process. So that means when sodium chloride forms from these two things, overall, that's going to be the energy that is released. That's the energy that is released. So why it's called a Born-Haber cycle is this actual cycle that I put in your notes. Then I'm going to kind of add to what we talked about here. Okay, so all I'm going to do is put it in more of a diagram form, and that is why it's called the Born-Haber cycle. So I found this on the internet. I don't know where I got it from, but what I want you to focus on is on the left-hand side, this is where energy is going in. So you will see positive values over on the left. And then energy is coming out in this diagram on the right side, okay? So I'm going to label a couple of these because some of them are obvious, some of them are not. And I'm just going to start with the sodium solid plus 1/2 Cl2. I'm changing it to a gas. So I'm going back to what I call my heat of sublimation. So this is heat of sublimation. And that is the 108 kilojoules that we just talked about. This step going from the sodium to the sodium ion, this is ionization energy 1, meaning it's the first electron to come off. So this is ionization energy. And this is 496 kilojoules. Again, positive and positive. And then this step here, I'm going from 1/2 Cl2 to just Cl. And that is your breaking of bonds. So you're breaking Cl-Cl. That's about 122 kilojoules. So now if I look over on the right, I'm now changing Cl to Cl minus. So it's Ea, which is your electron affinity. And for this one, it's negative 349 kilojoules. And then if I were to go from the ions back down to the sodium chloride, and again, sodium chloride in the solid form is on here on the bottom. So this is the bottom of the diagram here. So if I have essentially, this is the lattice energy, but it is going in the reverse direction. So this is the lattice energy. This is negative 788 kilojoules. Okay, so what is the mystery? Okay, the mystery is here, okay? So it is going from, okay, the sodium solid plus 1/2 Cl2 gas goes to sodium chloride solid. That's what I want to find out. So since this arrow is pointing in the opposite direction, please understand that it's going to be a negative number. Okay. Secondly, if you were to add all of this up and subtract these from it, you will get the negative 411 kilojoules of energy. So the diagram itself is to help you organize what is taking place. And again, you're going to be missing one part of the picture. So you have to have all of these other parts to find one part, but what you have to be aware of is it going to release energy or is it going to require energy? And depending upon the direction of what you're looking at is what you're focused on. So this is called the Born-Haber cycle. So I'm going to have you do both the calculation and the diagram for these types of problems. And to finish up this idea of lattice energy, I've put this table in your notes to kind of give you some data. Sometimes I like to show you numbers so that it makes more sense as to the trends we're seeing or the behavior that we're seeing with these ions. So let's look at lithium, okay? And more specifically, let's compare two different ionic compounds. So let's look at lithium fluoride versus lithium iodide, okay? So since they are both containing lithium, the only difference between the two is the anions. So look at the amount of energy stored in lithium fluoride. It's 1036 versus lithium iodide, which is 757. Well, the reason for that is iodine is larger. So the distance between the iodine and the lithium has got to be much bigger than it is between lithium and fluoride. And since we know Coulomb's law again, we could say that if you have a shorter distance, you're going to have more energy or more attractive forces. Other thing I want to compare it to is, let's look at beryllium. So let's look at lithium fluoride versus beryllium fluoride. Okay, so if I look at the energies here, lattice energy, beryllium fluoride, there should be a 2 there. Beryllium fluoride, since beryllium is a +2 and lithium is a +1, I have a difference there. I have much more energy or lattice energy between the beryllium and the fluoride because this is a +2 versus a -1 versus is a +1 -1. Okay, so I could see that with the 3,505 versus the 1036 for that. So in general, lattice energy is going to be, again, looking at Coulomb's law. But we are going to, because all of these are solids, ionic solids, is what it exists at 25 degrees Celsius. So the higher the lattice energy, the melting point is going to be affected. So higher the lattice energy, the more stable the solid is going to be. So if I looked at lithium fluoride versus lithium iodide, I would see that lithium fluoride would have the higher melting point, okay? So lithium fluoride would have a higher melting point, okay? It is a more stable compound. Versus beryllium fluoride would also be the higher melting point because of that. So this is, again, following the trends we talked about, following Coulomb's law, all melted into one.